Chapter 4: Processing Architecture. And now for something completely different. The previous chapter presented the core ASP.NET Web API programming model, introducing the set of fundamental concepts, interfaces, and classes exposed by this framework. Before we address the book's core subject of designing evolvable web APIs, this chapter takes a short detour to look under the hood and present the underlying ASP.NET Web API processing architecture, detailing what happens between the reception of an HTTP request and the return of the corresponding HTTP response message. It also serves as a roadmap for the more advanced ASP.NET Web API features that we will be addressing in the third part of this book. During this chapter we will be using the HTTP request presented in example 4.1 as associated with the controller defined in example 4.2 as a concrete example to illustrate the runtime behavior of this architecture. eProcesses controller contains a get action that returns a representation of all the machine's processes with a given image name. Exemplifying HTTP request is a get on the resource identified by HTTP // localhost 50650 /API /processes. Name equals Explorer, which represents all the Explorer processes currently executing. Example 4.1. SAM. Pull HTTP request message get HTTP // localhost 50650 /API /processes. Name equals Explorer HTTP /1.1 user agent fiddler host localhost 50650 accept application /SAM. Example 4.2. SAM. Pull controller public class processes controller API controller. Public process collection state get string name. If string dot is null or empty name. Throw new HTTP response exception HTTP status code dot not found. Return new process collection state. Processes equals process. Dot get processes by name. Dot select equals new process state. Public class process state. Public ID get set. Public string name get set. Public double total processor time in millis get set. Public process state. Public process state process proc. ID equals proc.id. Name equals proc.process name. Total processor time in millis equals proc.total processor time total milliseconds. Public class process collection state. Public enumerable. Processes get set. The ASP.NET Web Processing Architecture, represented in Figure 4.1, is composed of three layers. The hosting layer is the interface between Web API and the underlying HTTP stacks. The message handler pipeline layer can be used for implementing cross-cutting concerns such as logging and caching. However, the introduction of O in this CUSID in Chapter 11 moves some of these responsibilities down the stack into O in middleware. The controller handling layer is where controllers and actions are called, parameters are bound and validated, and the HTTP response message is created. Additionally, this layer contains and executes a filter pipeline. Let's delve a bit deeper into each layer. Figure 4.1. Simplified ASP.NET Web API Processing Model. 1. OWIN hosting support was introduced in ASP.NET Web API, version 2. The hosting layer, the bottom layer in the Web API processing architecture, is responsible for the hosting and acts as the interface between Web API and an underlying HTTP infrastructure, such as the classic ASP.NET pipeline, the HTTP listener class found in the .NET frame, work system.NET assembly, or an OWIN host. The hosting layer is responsible for creating HTTP request message instances, representing HTTP requests, and then pushing them into the upper message handler pipeline as part of processing a response. The hosting layer is also responsible for taking an HTTP response message instance returning from the message handler pipeline and transforming it into a response that can be processed by the underlying network stack. Remember that HTTP request message and HTTP response message are the new classes for representing HTTP messages, introduced in version 4.5 of the .NET framework. The Web API processing architecture is built around these new classes, and the primary task of the hosting layer is to bridge them and the native message representations used by the underlying HTTP stacks. At the time of writing, ASP.NET Web API includes several hosting layer alternatives, namely self-hosting in any Windows process, for example, console application or Windows service. Web hosting using the ASP.NET pipeline on top of Internet Information Services (IIS). OWIN hosting using an OWIN-compliant server, such as Cortana 1. The first hosting alternative is implemented on top of WCF's self-hosting capabilities and will be described in Chapter 10 in greater detail. The second alternative of hosting this is the ASP.NET pipeline and its routing CA capabilities to forward HTTP requests to a new ASP.NET handler, HTTP controller handler. This handler bridges the classical ASP.NET pipeline and the new ASP.NET Web API architecture by translating the incoming HTTP request instances into HTTP request message instances and then pushing them into the Web API pipeline. This handler is also responsible for taking the returned HTTP response message instance and copying it into the HTTP response instance before returning to the underlying ASP.NET pipeline. Finally, the third hosting option layers Web API on top of an OWIN-compliant server. In this case, the hosting layer translates from the OWIN context objects into a new HTTP request message object sent to Web API. Inversely, it takes the HTTP response message returned by Web API and writes it into the OWIN context. There is a fourth option, which removes the hosting layer entirely. Requests are sent directly by HTTP client, which uses the same class model, into the Web API runtime without any adaptation. Chapter 11 presents a deeper exploration of the hosting layer. Message handler pipeline. The middle layer of the processing architecture is the message handler pipeline. This layer provides an extensibility point for interceptors that addresses cross-cutting concerns such as logging and caching. It is similar in purpose to the middleware concept found in Ruby's wrap, Python's WSGI web server gateway interface, and the Node.js Connect framework. A message handler is simply an abstraction for an operation that receives an HTTP request message instance and returns an HTTP response message HTTP response message instance. The AskNet Web API message handler pipe line is a composition of these handlers, where each one except the last has a reference to the next, called the inner handler. This pipeline organization provides a great deal of flexibility in the type of operations that can be performed, as depicted in Figure 4-2. Figure 4-2. L. Message handler processing examples. The diagram on the left illustrates the usage of a handler to perform some pre- and post-processing over request and response messages, respectively. P. Processing flows from handler to handler via the inner handler relationship in one direction for request processing and in the reverse direction for response processing. Examples of pre- and post-processing are changing the request HTTP method, based on the presence of a header such as XHTTP method override, before it arrives to the controller's action. Adding a response header such as server. Capturing and logging diagnostic or business metric data. You can use handlers to short-circuit the pipeline by directly producing an HTTP response, as shown on the right side of Figure 4-2. A typical use case for this behavior is the immediate return of an HTTP response with a 401 unauthorized status if the request isn't properly authenticated. In the .NET framework, message handlers are classes that derive from the new HTTP message handler abstract class, as shown in Figure 4-3. Figure 4-3. Me. Sarge handler class hierarchy. The abstract sendAsync method receives an HTTP request message and asynchronously produces an HTTP response message by returning task. This method also receives a cancellation token, following the tap task asynchronous pattern guidelines for cancelable operations. The message handler pipeline organization just described requires a data member to hold a reference to an inner handler as well as data flow logic to delegate requests and response messages from a handler to its inner handler. These additions are implemented by the delegating handler class, which defines the inner handler property to connect a handler with its inner handler. The sequence of delegating message handlers that constitute the pipeline is defined in AskNet Web API's configuration object model on the HTTP configuration.message handlers collection property. For example, config.messagehandlers.add new trace message handler. The message handlers are ordered in the pipeline according to the config.messagehandlers collection order. AskNet Web API 2.0 introduces support for the OIN model, providing the OIN middleware as an alternative to message handlers as a way to implement cross-cutting concerns. The main advantage of OIN middleware is that it can be used with other web frameworks, for example, AskNet MVC or SignalR, since it isn't tied specifically to Web API. As an example, the new security features introduced in Web API 2.0 and presented in Chapter 15 are mostly implemented as OIN middleware and reusable outside of Web API. On the other hand, message handlers have the advantage of also being usable on the client side, as described in Chapter 14. Route dispatching. At the end of the message handler pipeline, there are always two special handlers. The routing dispatcher implemented by the HTTP routing dispatcher class. The controller dispatcher implemented by the HTTP controller dispatcher class. The routing dispatcher handler performs the following. Obtains the routing data from the message, for example, when web hosting is used, or performs the route resolution if it wasn't performed previously, for example, when self-hosting is used. If no route was matched, it produces a response message with the 404 not found HTTP status code. Uses the route data to select the next handler to which to forward the request, based on the match type route. The controller dispatcher handler is responsible for using the route data and a controller selector to obtain a controller description. If no controller description is found, a response message with the 404 not found status code is returned. Obtaining the controller instance and calling its execute async method, passing the request message. Handling exceptions returned by the controller and converting them into response messages with a 500 internal error status code. For instance, using the HTTP request of example 421 and the default route configuration, the route data will contain only one entry with the controller key and process S value. T. His single route data entry is the result of matching the HTTP // localhost 50650 API /processes name equals Explorer request URI with the /API /controller /ID route template. By default, the routing dispatcher forwards the request message to the controller dispatcher, which then calls the controller. However, it is possible to explicitly define a pairout handler, as shown in Figure 424. Figure 424. A. Are route handlers and the route dispatch handler. In this case, the request is forwarded to the handler defined by the route, not to the default controller dispatcher. Reasons for using per route dispatching include flowing the request message through a route-specific handler pipeline. A concrete example is the use of distinct authentication methods, implemented in message handlers, for different routes. Another reason for using per route dispatching is the substitution of an alternative framework for the Web API top layer controller handling. Controller handling. The final and uppermost layer in the processing architecture is the controller handling. This layer is responsible for receiving a request message from the underlying pipeline and transforming it into a call to a controller's action method. Passing the required method parameters. It also is responsible for converting the method's return value into a response message and passing it back to the message handler pipeline. Bridging the message handler pipeline and the controller handling is performed by the controller dispatcher, which is still a message handler. Its main task is to select, create, and call the correct controller to handle a request. This process is detailed in Chapter 12, which presents all the relevant classes and shows how you can change the default behavior using the available extensibility points. The API controller base class, the concrete controller that ultimately handles the request, can directly implement the IT controller interface. However, the common scenario, as presented in the previous chapter, is for the concrete controller to derive from the abstract API controller class, as shown in Figure 425. It is the job of API controller.execute async to select the appropriate action, given the HTTP request method, for example, get or post, and call the associated method on the derived concrete controller. For instance, the GET request in example 421 will be dispatched to the process's controller.getStringName method. Figure 425. Concrete controller deriving from the abstract API controller class. After the action is selected but before the method is invoked, The API controller class executes a filter pipeline, as shown in Figure 4 to 6. Each action has its own pipeline composed of the following functionalities. Parameter binding. Conversion from the actions return into an HTTP response message. Authentication, authorization, and action filters. Exception filters. Figure 4 to 6. Per action filter pipeline, parameter binding, and result conversions. Parameter binding is the computation of the action's parameter values, used when called in the actions method. This process is illustrated in Figure 4 to 7 and uses information from several sources, namely the root data, for example, root parameters, the request URI query string, the request body, the request headers. Figure 4 to 7. Parameter binding. When executing the actions pipeline, the API controller.execute async method calls a sequence of HTTP parameter binding instances, where each one is associated with one of the actions method parameters. Each HTTP parameter binding instance computes the value of one parameter and adds it to the action arguments dictionary in the HTTP async context instance. HTTP parameter binding is an abstract class with multiple derived concrete classes, one for each type of parameter binding. For instance, the formatter parameter binding class uses the request body content and a formatter to obtain the parameter value. Formatters are classes that extend the abstract media type formatter class and perform bidirectional conversions between CLR common language runtime types and byte. 2. The action result interface was introduced in version 2.0 of Web API. Stream representations, as defined by Internet media types. Figure 4 to 8 illustrates the functionality of these formatters. Figure 4 to 8. For are matters and conversions between message bodies and CLR objects. A different kind of parameter binding is the model binder parameter binding class, which instead uses the concept of model binders to fetch information from the root data in a manner similar to ASP.NET MVC. For our instance, consider the action in example 4 to 2 and the HTTP request in example 4 to 1. The name parameter in the get method will be bound to the value explorer, that is, the value for the query string entry with name key. We LL provide more detail on formatters, model binding, and validation in Chapter 13. Conversion into an HTTP response message after the action method ends and before the result is returned to the filter pipeline. The action result, which can be any object, must be converted into an HTTP response message. If the return type is assignable to the action result interface 2 presented in example 4 to 3, then the results execute async method is called to convert it into a response message. There are several implementations of this interface, such as OK result and redirect result, that can be used in the actions code. API controller base class also includes several protected methods not shown in Figure 4 to 5 that can be used by derived classes to construct action result implementations, for example, protected internal virtual OK result OK. Example 4 to 3. Heap action result interface publish interface heap action result. Task. Execute async cancellation token. If the return isn't a heap action result, then an external result converter, implementing the action result converter interface as defined in example 4.4, is selected and used to produce the response message. Example 4.4. Res. Alt converters converting the actions returned into response messages publish interface action result converter. HTTP response message convert. HTTP controller context object action result. For the HTTP request in example 4.1, the selected result converter will try to locate a formatter that can read a process collection state, i.e., the type returned by the actions method, and produce a byte stream representation of it in application /JSON, i.e., the value of the request's accept header. In T. End, the resulting response is the one presented in example 4.5. Example 4.5. HTTP. Response HTTP /1.1200 OK cache control no cache pragma no cache content type application /JSON. SHA-SIT equals at 8 expires -1 server Microsoft IIS /8.0 date due, the 25th of April, 2013 115,012 GMT content length. Processes ID 2824 Name Explorer, total processor time in millis 831.656.9311. Formatters and content negotiation are addressed in more detail in Chapter 13. Filters, authentication, authorizations, and action filters are defined by the interfaces listed in example 4-6, and have a role similar to message handlers, namely, to implement cross-cutting concerns, for example, authentication, authorization, and validation. Example 4-6. F. Filter interfaces publish interface iFilter. Do allow multiple get. Publish interface authentication filter iFilter. Task authenticate async. HTTP authentication context cancellation token. Task challenge async. HTTP authentication challenge context cancellation token. Publish interface authorization filter iFilter. Task. Execute authorization filter async. HTTP action context cancellation token, func. Continuation. Publish interface action filter iFilter. Task. Execute action filter async. HTTP action context cancellation token, func. Continuation. Publish interface exception filter iFilter. Task execute exception filter async. HTTP action executed context, cancellation token. For authorization and action filters, the pipeline is organized similarly to the message handler pipeline. Each filter receives a reference to the next one in the pipeline and has the ability to perform pre- and post-processing over the request and the response. Natively, the filter can produce a new response and end the request immediately, thereby short-circuiting any further processing, namely, The actions invocation. A. U. Authentication filters operate under a slightly different model, as we will see in Chapter 15. The main difference between authorization and action filters is that the former are located before parameter binding takes place, whereas the latter are located after this binding. As a result, authorization filters are an adequate extension point to insert operations that should be performed as early in the pipeline as possible. The typical example is verifying if the request is authorized and immediately producing a 401 not authorized HTTP response message if it is not. On the other hand, action filters are appropriate when access to the bound parameters is required. A fourth filter type, exception filters, is used only if the task returned by the filter pipeline is in the faulted state, that is, there was an exception. Each exception filter is called in sequence and has the chance to handle the exception by creating an HTTP response message. Recall that if the controller dispatcher handler receives an unhandled exception, an HTTP response message with a status code of 500. Internal server error is returned. We can associate filters to controllers or actions in multiple ways. Via attributes, similarly to what is supported by ASP.NET MVC. By explicitly registering filter instances in the configuration object, using the HTTP configuration.filters collection. By registering a file to provide an implementation in the configuration services container. After the HTTP response message instance has left the action pipeline, it is returned by API controller to the controller dispatcher handler. Then it descends through the message handler pipeline until it is converted into a native HTTP response by the hosting layer. Conclusion. This chapter concludes the first part of the book, the aim of which was to introduce ASP.NET Web API, the motivation behind its existence, its basic programming model, and its core processing architecture. Using this knowledge, we will shift focus in the next part to the design, implementation, and consumption of evolvable web APIs, using ASP.NET Web API as the supporting platform. Chapter 5. The